we ready? Hi, I hope everybody has had good lunch and that you guys had enough coffee because we have a really exciting talk. It is my pleasure to introduce Martin Hiller from Volvo Cars, and where he's been for the last 2 years. He also has a PhD from Chalmers, so you know, definitely a local person. He has an exciting talk about his role in Volvo, where he's actually one of the technology leads in software architecture. And the talk is going to be focused on what he and his group are doing to prepare Volvo for the software changes that are coming in car manufacturing, and also how he's actually changing the philosophy of a company that was historically mostly mechanical engineering based to adapt and adopt to the challenges of software centric development of cars. So with that, Martin, the stage is yours.
Thank you very much for that very nice introduction. Builds no pressure at all. Exciting talk and all that. We'll see. Right, so my name is Martin Hiller from Volvo Cars. We are right now conducting a study on what the next generation electronic architecture should be in our vehicles. And I'm going to talk about the journey that we took from when everything started to where we are today, and the next steps that we think that we have to take to cope with that new future. So I hope it will be, if not entertaining, at least informative to some degree. So, and afterwards, feel free to ask questions. So I'll start with talking a little bit about this picture, though. This was taken on April 14th, 1927, so in 9 days. This is a 90-year-old picture. This is the very first Volvo car that was built in the factories that are, well, this building is now roughly 5 minutes from here. It's still used for vehicle development, but it's part of the Volvo Trucks part right now, so no cars coming out of that building anymore, but it's still active in the automotive engineering world. So it's quite interesting. So, but since then, stuff has happened. So now we build a little bit more than 500,000 cars a year. We are 31,000 plus some change people across the globe, and we are active mainly in the Americas. Right, that was the next picture. Mainly in the Americas, in Europe, and in China, in Asia. So that was the corporate stuff that always has to be there. Let's look at the cars through the years. So we started out with actually some very nice looking cars. So in the 50s and 60s, Volvos were very beautiful cars. In the 70s, oh right, no, this is still in the 60s. So this is the, for those of you, I don't know, you look so young, so you haven't seen The Saint on television. He drove a P1800, a Volvo sports car from the 60s. One of the most beautiful cars that Volvo has built. In the 70s, something happened. Not sure what. And in the 80s, we found a box of rulers. So everything was straight. But the cars were strong. So extremely safe. In the 90s, we threw out the rulers. Things became a bit more soft, round edges. And stuff progressed from there to maybe not stunning, but at least not extremely ugly. And these are the cars we have now, and these are extremely beautiful, if you ask me. So we're very proud of the lineup that we have today. So now we're finally, after 90 years, back to building beautiful cars. So that's nice. But let's get back to the beginning. So this is the very first Volvo, the Volvo that you saw driving out of that building in the first picture. It's called Jacob. I'm not sure why the serial number here is 4. If it's the 4th generation, why is it the first car? I don't know. If we look at the electrical system of this, it looks something like that. Not very complex. So here you have, the headlights, the horn, a battery, taillights, and some other small components. There has been some progress since then. If we look at the computerization of vehicles from the 70s and onward, it has been quite a trip. It started with powertrain-related mechanical components, so the engine and the transmission, fuel injection. They were all computerized fairly early. For Volvo, it was somewhere in the 70s. In the 80s, or I should say in the 70s, they were still single components, so they didn't have much communication between each other. In the 80s, there was some intercommunication between these, hardwired. We started to get a cruise control. We started to get a more coordinated powertrain control. And in the 90s, we got traction control. So we started to computerize the chassis as well. Adaptive suspension came along in those years as well. And then mid-90s somewhere is a kind of a flex point. That's where we introduced multiplex networking, so kind of a modern network in the car. And in this case, for Volvo, it was the first CAN-based vehicle network. And from that point, things have just skyrocketed when it comes to computer control. So we got navigation systems in the late 90s, early 2000s, stability control, adaptive cruise control with radars and cool stuff like that came in end 2000 or mid 2000 maybe. We started to do some collision mitigation, collision avoidance, and now we're into the more advanced driver assistance systems. Cars are starting to be able to drive themselves. So that's really the next step to the autonomous cars. And if you look at this curve, this tries to indicate the share of the total cost or the total value of a vehicle that is related to electronics and software. So starting out fairly low in the 70s, around 5%, right below that. We see that, well, right now we're up to around 45% maybe. And over the next decade, we will, by a good margin, cross the 50% threshold. So half of the cost or half of the value of a vehicle will be the electronic and software content. And that's quite a shift. So the, how should I put this? The industry as such hasn't really kept up with this development. So the management of the various automotive companies, they're still very much into the mechanical and mechatronic world. And all this transition to an electronic and software-defined product has kind of crept up on them from behind. But now we're actually getting into the next decade with a lot more confidence in that department, and I will talk to you more about that. But first, I would like to place vehicles in a context, in the context of other software-intensive systems. And I'd like to bring up those systems that perhaps people think of most when they think of advanced electronically controlled, computer-controlled systems, spaceborne systems, and aeronautical systems. So we have here, in the Space Department, we have the Space Shuttle, retired now, but still, it's an interesting system to look at. We have the International Space Station, still active, and we have Orion, which is the replacement of the Space Shuttle, still in development by NASA. On the Aeronautical Department, we have the flagship products from Boeing and Airbus, the Boeing 787 and the Airbus A380, their most modern aircraft. And from the military side, we have the F-35 Lightning, which has been deemed as the most complex aircraft ever built. Basically a computer on wings, as they say. So we'll see how a car fares to these systems. I'm going to take a look at lines of code without going into any discussion on whether lines of code is a good metric of size or complexity, but it gives you a kind of a ballpark of how big are these sizes or these systems from a software point of view. So the first one is the Space Shuttle, roughly 400,000 lines of code. But you know, it's an old system. It was built some 40 years ago. It's okay to not have that much software. The next one is International Space Station, so with 2.3 million. I think we'll have to change the scale there a little bit. So that's the software that is keeping the International Space Station in orbit. Doesn't count all the experiment and all the other stuff that is up there. It's just the control software of the space station. It's roughly 2.3 million lines of code. Next one, Orion, also 2.3. But it's in development, so they still have potential to grow that, I guess. Okay, so the spaceborne systems are actually there's not that much software that is critical in those, which is probably good, because they're kind of tricky, not a good safe state. Right, so we have the aircraft. The first one there is the Boeing 787 at 14 million lines of code. Now we're getting somewhere, but we'll have to change the scale a little bit more. So we have the two contenders for the top place here. We have the Airbus A380 civilian aircraft, or we have the military aircraft, the F-35 Lightning. I will not hold you in suspense any longer. The second place goes to the F-35 at 24 million lines of code. So is this a tight race, or is it a clear winner? It's actually a fairly clear winner. 100 million lines of code. I'm not sure what they do with all all those lines of code, but it's a lot of software. Yeah. So the question now is, where does a car fit on this scale? Is it closer to the spaceborne systems or closer to the aircraft systems? Well, maybe you'd be surprised, but we're actually in that ballpark, somewhere between 50 million and 100 million lines of code in a modern high-end car today. And that number is a few years old. So it's growing steadily. So you'll be sure that we will, in a fairly short time, we will have overtaken the aircraft when it comes to size of the software in the vehicles. Well, I hope that was kind of an eye-opener. Next time you get into a car, think about that. If we look at how the software has evolved at Volvo over the past 20 years, I'm not going to look at lines of code, but I'm going to look at the amount that we download in the car. So this is downloadable software in the cars. And it looked something like this. So 20 years ago, roughly, we had 1.5 megabytes downloadable code. So it fits on a, I don't know if anyone remembers those 3.5-inch discs at that point. It's almost kind of cute. But we've seen over these years that every 5 to 7 years, which coincides with generational steps in the automotive industry. So every 5 to 7 years, there is a generational step. We see that the software content, or at least the parts that we can download, grow with a factor of 10. So right now we are at, if we were to include the speech and maps information, this is not speech and maps information in the latest models, but if we were to include that, we are at 1.5 gigabyte downloadable data. Multiplying that was 2014, so the next 5 to 7 years, the beginning of next decade, we will have roughly 15 gigabyte that we can download into the cars. So it's a tremendous amount of software and data that goes into the vehicles. Looking at the number of ECUs, the electronic control units, also the same period. It's a steady growth from around 20 years ago to more than 100 today. Many of these are small nodes, but still there are nodes that have some kind of software in them that has to be managed. So extrapolating this, you see it's a steady growth over the past 20 years. It's not really something that we can sustain for very much longer. And actually looking at our competitors, some of them have even more nodes in their cars. Some are up to 200. I'm not going to tell you who they are, but they are built in the south of Germany. So, bus signals. You know, we have all this electronic equipment has to interchange information with each other. So we have a number of networks. High-speed networks, mid-speed networks, and low-speed networks. And the bus signals are all that information that flows on these networks. So that's also quite a development. 20 years ago, we had a few hundred, maybe up to 1,000 signals that were sent across 2, maybe 3 networks. And the newest cars, those that were introduced a couple of years ago, the first models had around 7,000 of those system signals transmitted over maybe a dozen or so main networks. And if we look at our prototypes for autonomous vehicles, that information is already doubled. So we're up to 14,000 signals. And we see that this is steadily increasing. So where does this take us? If we go back to 1927, this was the electrical system of the first Volvo. This is the topology that we have today, the 100 nodes and all the networks. But you know, this is not really an electrical schematics. These are only the high-level nodes and the high-level networks tidily laid out into a nice topology view. If we take a look at the reality, it looks like this. You can actually make out the shape of the car by just looking at the cabling. That's kind of interesting. So it's quite a complex system that we're building. And it's just going to get worse. So what is coming up next? Let's take a look at that. Autonomous cars, of course. Volvo prides itself to be one of the main developers of technology for autonomous cars. We have, or we will have, autonomous cars running around on the streets of Gothenburg by the end of this year, is the plan. And that will then spread across the world, all in research projects, prototypes, so they're not, you cannot buy these yet. But in a few years' time, you will be able to do that. So somewhere between 2020, 2025, there will be the first autonomous cars available for purchase. Connected cars. Well, the cars will be connected to the internet. I will go more into detail about the implications of these things in just a few slides. So there will be a very high bandwidth link to the internet from all of these cars. We see that there are some new players coming that want to play in this area. Players that don't have a background in traditional automotive industry. And that's kind of interesting. And we also see new customer expectations. Over the past 10 years, customers have, or people around the world have a completely different relationship to consumer electronics than they had 10 years ago, and that's starting to spill over into our industry as well. So these two will affect the technology in our products. What is it we build into the cars? Whereas these two will mainly affect how we work and what skills we need to have in order to survive in the future. So let's go into some more details. Autonomous cars. There is a ladder where you place different levels of autonomy. So levels 1 and 2, those are the systems that we already have today. You have cruise control, adaptive cruise control, maybe you have some line keeping aid or line departure warning. Things that help you as a driver to operate the vehicle in a safe manner. Level 3 is conditional automation, which means that in some certain situations the car can drive basically on its own. This is where Tesla is today with their autopilot. It's on level 3. But if we look at the higher levels, levels 4 and 5, called just high automation and full automation, the main distinction between levels 1 to 3 and levels 4 and 5 is that in the lower levels, the driver is still responsible for what the vehicle does. So in that case, all these advanced driver assistance systems are only there for your convenience. You still have the responsibility. But as soon as we go to level 4 and 5, you're actually relieved of that responsibility. As soon as you activate that function, the car will be responsible for what it does. And an extension, the car manufacturer will be responsible for what the car does. Good or bad. And this is where we want to be, of course. Shouldn't be easy. And this is actually taking it one step further than our aeronautical friends. If we look at the autopilots today in aircraft, they don't relieve the pilots of any responsibility. The pilots are still responsible for what the aircraft does. But we'll take it one step further. So it's a bit of a challenge. Not everyone has really grasped what kind of a change this actually is. But we're getting there. So what does this mean for the technology? Well, we have lots of sensors. I think in the prototypes we have some 30 different sensors that, with different technology, read the surroundings of the cars. We have cameras, we have radars, we have LiDARs, that is laser scanners, we have ultrasonic sensors, lots of different sensors that provide data of the surroundings in the car. So that amounts to huge amounts of data. And all this data has to be sent quickly to the processing algorithms that try to make any sense of this. So of course there will be a need for a lot of communication in those cars. Safety first. A classical vehicle today is mainly built on the fail-safe approach. So if anything should fail in the system, we just go to a safe state. And in many cases today, the safe state is to just inform the driver that, whoops, we cannot activate this function, or I have deactivated, so you will have to take control. That's not really something we can do when it comes to autonomous cars. We have to go to a fail operational state. So the electronic system and the electronic control has to be available at all times. Cloud communication. Lots of information will be exchanged between the autonomous cars and the cloud. So we will download, for example, a very high definition map of the surroundings. And this is not your ordinary navigational map. No, this is more of a map that shows you, or that shows the sensors what they should see. So we can compare what the sensors see with this high definition, almost like a point cloud map of the surroundings. And that will help us to pinpoint exactly where the vehicle is. We'll download lots of traffic info, real-time traffic info, and we will upload vehicle behavior. We will upload what the vehicle sees around it, the surroundings and the environments. There's a lot of data going up and down. And for that, of course, we want to have fairly high security in place. You don't really want to get this car hacked and controlled by someone somewhere else. That would be quite scary. There will be lots and lots of logging in these cars. Remember, I said that the driver is no longer responsible, but we are. And of course, we want to know what actually goes on in these vehicles. So if something should happen, we want to know exactly what happened in those vehicles. So there will be lots and lots of data that is going to be logged on what the vehicle does and also on what the driver does. Machine learning. We've come to a conclusion that in order for these algorithms to adapt and to learn how to drive a car, we will have to employ machine learning at some stage in the development. This does not mean that the algorithms themselves in the car will be machine learning algorithms that adapt to how you drive. It's more like the way we analyze how vehicles behave that will help us get information on how to better develop these autonomous algorithms. So that will be, machine learning will play a big role in the future cars. And that's not only for autonomy. Software update. The best way to get quality and to get safety and security is to be able to quickly update the software if you find something that is wrong. In a traditional car today, that's not really possible. You get maybe a software update when you take your car to the garage for some service or maintenance. There are a few exceptions, notably Tesla is very far ahead in this game, so they have over-the-air updates of their cars. But it's something that we still have to work on a little bit. So looking at the connected cars, we see that the car will be more or less an extension of your digital self or your living room or your office or whatever. So the connection to the internet has to be stable, has to be transparent, and you will have lots of different services that make use of this link. Of course, entertainment, watching movies, listening to music, all that kind of stuff. Safety information, you want to get the information from what goes on in traffic around you. Are there any accidents? What's the weather like ahead? Are there any spots that are a bit slippery? All that kind of information. You want to really personalize your car, so you want to have your own settings, personal settings. You want to have your own services. You want to have your own, all those things that you have on your phone. You really want to have these mirrored onto whatever you have in your car as well. You will get information from all kinds of blue light emergency services, so police cars, ambulance, fire departments. That kind of information, local information, will be received by the cars. So you will know if there is a police approaching or an ambulance or whatever. You will talk to other vehicles to exchange information about, for example, slippery patches on the road, to exchange information on what is the intent of the vehicles ahead of you. Will they turn left, turn right, brake, all that kind of stuff, in order for your vehicle to be able to adapt to those maneuvers. And you will also communicate with the infrastructure. So the car will communicate with red lights, with traffic signs, with all kinds of infrastructure processes or components. So what does that mean? Well, it means we have multiple access points that are wireless. We will have 4G access, 5G access, and whatever G access comes in the future. We will have Wi-Fi, Bluetooth, and also there, whatever wireless technology will come in the future, the car will surely have it at some point. Again, with the data, all these ones and zeros, all these bits have to be transported. So it's lots of data that goes up, that goes down, and that goes around inside the car. High bandwidth is a necessity for that. Something that is new to cars is user management. You will have to log into your car to get access to all the cool cloud-connected services, and to move your personal settings from one vehicle to another vehicle. So there will be some kind of a user management requirement. And security, of course. This is really, this is perhaps the most tricky part. It's not something that we are traditionally very good at. But with these connected services, and especially in combination with autonomous cars, security will maybe be the most difficult nut to crack. And that goes, I mean, all the different flavors within security have to be in place. You have to have integrity, authentication, privacy, confidentiality, all that stuff. Actually, the privacy discussion is something that is very vivid in the automotive industry today. Who owns the data that is generated by the car? Is it you as the owner? Is it the driver? Or is it the manufacturer? Different manufacturers have different takes on that, and the discussion is still fairly ongoing. So, from a technology point of view, what does this mean? Well, it means basically we have to build a computer on wheels. And that, in this audience, that may not sound as a very big leap, but if you go to the traditional automotive manufacturers, they don't really see this. But we have to take this step from building a computer-like car to instead build a car-like computer. I sometimes joke with my mechanical colleagues that the chassis is just something that keeps the electronics, or that holds the electronics. They don't really get that joke. They don't see it that way, but they're coming around. So, I will talk to you a little bit about the directions that we see when we look at the future electronic architecture in the vehicle, or at Volvo at least. I saw some of my colleagues here in the audience, so approach them later after this talk to get how it really looks. So, but anyway, this is the main direction. We will have in the vehicle a core computer system that consists of ECUs, or computers basically, that just run software, that just are good at running whatever kind of software that we throw at them. They don't have to care about mechatronic IOs and all those low-level control stuff. They just run software. So basically, high-power PCs in your vehicle. So these are the central components, the vehicle computation units. Around that, we will have a cluster of connection points, basically, or integration points. These are the VIUs out in the corners. So this is where we connect all the mechatronic equipment in the vehicle. And these core components, they will be connected in a high bandwidth network, which most likely will be an automotive flavor of Ethernet. So in the first generations, maybe 100 megabit Ethernet, but fairly soon we will get up to gigabit speed in that network as well. And around that, we will have the more classical automotive electronic units. So these are the units that control the engine, that control the brake system, that control your steering column, that control your doors, your windows, your seats. All these basic mechatronic capabilities will be connected to one of these integration points. So it will be basically just like plugging in your mouse or your external DVD player into your computer. It's the same kind of a principle. So we have a number of peripherals in the mechatronic rim, and then we have the core system that kind of provides all the high-level functionality. Yeah, that's just what I said. So these will be the specialized, specific control modules. Here we have the interface modules, basically like a device driver in your computer today. And this is where we have all the vehicle-wide management, vehicle-wide coordination, all the functionality that kind of faces you as a customer and makes use of all the mechatronic, the basic capabilities in the mechatronic rim. So going into some more details about the core system software stack, we see that there is a necessity to have different operating systems depending on what kind of functionality you want to put in that core system. So one way to enable that is to have at the foundation some kind of a partitioning kernel, a hypervisor of some sort. Most likely a type 1 hypervisor, a very thin layer of software that provides this partitioning of the resources in the core system. And in each partition, we can then place a more high-level operating system or a software platform that is most suited for that kind of application or that kind of functionality that goes into that partition. Since we have this tight partitioning in place, we know that each partition gets its share of the resources. So you will have the computational power that you were promised, you will have the memory that you were promised, and all of that will help us to decouple the development of all these applications, of all these software stacks that have to be integrated onto the same hardware. Without this kind of a partitioning, I don't think it would be feasible to have all the software in one system. And this partitioning also enables us to place software with mixed criticality on the same hardware. If we wouldn't have had this partitioning in place, the highest criticality software kind of transforms or colors or poisons all the other software stacks as well. So we'll have to develop everything to the highest level of criticality that you have in the system. So this is really a key piece of the puzzle to have this partitioning in place. When it comes to, the automotive industry has built software for 30 years, 40 years maybe. But we're still kind of in the learning stage of how to build software-intensive systems on this scale to get the overall coordination going. Our suppliers are, in many cases, a lot better at software development than the manufacturers are. We're good at integrating and getting stuff at low cost. But when it comes to development of these distributed systems, we still have some things to learn. And one thing to guide the software development is, of course, to use patterns of different kinds that guide the solution of how we divide our software. And I'm just going to briefly show you two of the main patterns that we see in our system, or that we want to employ in our system. And they're not really high-tech in any way, fairly well-known patterns in the software industry. The first one is layered architecture, which makes sense, right? We have the low-level mechatronic components providing us with the basic capabilities of what we want to do in a vehicle. We have a layer that kind of provides an overall control of maybe a few of those basic capabilities. And then we have the top layer, which is the overall management, the overall coordination, and the overall application that makes use of all these different fundamental capabilities in the vehicle. And something that we have today that kind of hinders us in the evolutionary pace is that we have crosstalk on the component level in the lowest layer, which kind of is a big no-no, really. But we do that, and we see the consequences of that. And that's something that we, in the next generation, really want to get better at, to shape up that kind of part. The next pattern is really an instantiation or a variant of the pipes and filters pattern. We see that every function in a vehicle, or basically every function in an embedded system, is something like this. You have mainly three phases. The first one is a perception phase, where the system gathers information of the sensors around it to make sure that we have a good picture of what goes on. Then we make some decisions on what we need to do in order to fulfill our mission, and then we actuate that in the action phase. So these two, the layered structure and this kind of a functional chain or pipes and filters variant, are the two main patterns that we want to employ when we build our system. Now, to the more how we work and what skills we need part, we see the new players from Silicon Valley mainly. Tesla is already up and running and has been so for 10 years. They're still in the red, but I think they are a force to be reckoned with. We know that Google has been working on autonomous cars for at least a decade. And what they will do, if they will start to build cars or if they will partner with someone, we're not really sure, but we know that they're coming. And there is a lot of smoke about Apple and their car project. It's really an on and off kind of a thing. But where there's smoke, there's fire, they say. So I'm sure that we will see in the next decade or so, we will see something from them as well. And there are lots more companies in Silicon Valley, startups, bigger companies that are attempting to try their luck in the automotive industry. And these guys really know their ways around computers and software. I mean, you could even say that they invented computers and software, so of course they know this. So what do they have that we don't have? Well, they have stable platforms that evolve over time. None of this generational, every 5 to 7 years there is a new generation. No, our platforms grow steadily on a yearly basis, maybe even. They're already agile. They know all about this continuous integration, continuous architecture, continuous development. So of course they know this. They're good at software architecture, software design. Some are better than others, but they know this. They're fairly good at designing user interfaces that are easy to understand and responsive. Again, some are better than others at this, but overall they're pretty good at this. They are really heavily invested in machine learning and all other cool software stuff that is coming along the line. Most of it comes from Silicon Valley, so they, of course, know all that already. They know security pretty well. And they know cloud services really well. So all of the things that we still have to learn, they have this already in their back pocket. What they don't know is how to fix the metal around the computers. But yeah, well, take a guess. Which part is the most difficult to learn, this or the metal part? Okay, so the customer expectations. We have, over the past 10 years, seen this surge in people using consumer electronics. Everyone has this little computer in their pocket now. Thanks, smartphone, yeah. There we have this easy-to-use, responsive UIs. You don't want any laggy UIs. You don't want something that is hard to understand. You don't tolerate crashes. You don't want blue screen of death on your car. You want this to be up and running all the time. You want to be able to personalize your experience in the car. And you crave, you should say, regular over-the-air updates of your software. Perhaps not if you have an Android phone, but if you have an iPhone, you get that regularly. You have instant on. I mean, you press a button and your device is on. And you're living with connectivity. It's a fundamental and transparent characteristic of your pocket computer. So all of that is also something that we have to get going in the vehicles. And this creeps into the automotive domain as well. Very much thanks to Tesla, because they've taken this into their cars already. So what does this mean for us? Well, we really have to become a software house. We have to become a software developer on par with those guys in Silicon Valley. And for Volvo Cars' part, we have embarked on an agile transformation that goes throughout the entire organization. So we want to get into agile software development, continuous integration, continuous deployment, continuous architecture, continuous everything, basically, which is actually the complete opposite of what we're doing today. So it's quite a challenge to get the organization going for this. We need to have one common code base. Right now we have, for different vehicles, different projects, we basically have different code bases. Or we have variants of the same code base. There is no main track. And we really need this main track if we want to have a chance at fighting this complexity and this functional growth. We have to invest heavily in automated testing. We do a lot of automated testing already today, but it's not nearly enough. So all this continuous integration, daily builds, and all that is something that we really need in order to get going. And I think it was Jeff Bezos at Amazon who coined this two-pizza team term. This is really something that we need to shoot for. If your agile team is bigger than you can feed on 2 pizzas, the team is too big. So that's something, it's kind of a guideline. We're not sure what kind of pizzas, if it's the American huge pizzas or if it's more the Billy's pan pizza, you know, this kind of shrunken thing that you get in a freezer, but at least no more than 2. And this transformation is a bigger challenge actually than the technology challenge. And I would just like to end this with a quote from maybe one of the best movies of all time. From Top Gun, you know, I feel the need for speed. And that's really what we need here in our industry. Thank you very much for your attention.
Thank you for this great talk. Are there any questions from the audience? Here's the mic. Over there.
Yes, concerning your patterns, do you already have a view on what kind of databases or data stores will be in the car? So database technology, how much is stored in the car?
How much will be stored? There will be a lot of data stored in the car. Sorry?
Which technology?
We haven't really come to that point yet in the architecture development. I don't think it will be a SQL database.
There's a question here with Patricia.
Thank you. Thank you for the very interesting talk. I was wondering, you have a lot of exciting challenges. Do you have a roadmap? So what is the first one or two in software architecture or software engineering that you are going to invest?
One activity that we're heavily invested in right now is to get continuous integration up and running. We have, over the past 6 months, started the build-up of our continuous integration team and are gradually getting all the different teams from the different nodes into that structure. And we're also trying to get our suppliers to deliver their software into our continuous integration machine. It's a slow progress, but there is progress nonetheless. So I would see that is the thing that we spend most of our effort at right now. And the next would be to, there's so much to do. I mean, the agile development of software creeps also into the commercial aspects. How do we write our contracts with our suppliers? Traditionally, the contracts are very waterfallish, if you will. We are expected to deliver a huge trunk of requirements at the beginning of the projects, and then some maybe 4 or 5 points along the line of development, they come with some delivery of software that hopefully works. So getting all that kind of agile working into the supplier landscape is also something that we're looking deeply into, how to get that going.
There's a question over there, and while they're bringing the mic, can you actually tell us how much of the overall sort of software that you guys envision when you get to the levels 4 and 5 you expect to kind of contract out versus build in-house?
That was an interesting question. I think it was on Saturday, the official start of a new company called Zenuity, which is a company partly owned by Volvo Cars and partly owned by Autoliv. Autoliv are known for airbags and all that kind of stuff. They will do the development of the algorithms when it comes to autonomous drive for us. So we've kind of located the expertise from the suppliers and our expertise in that area into the same company. So it's kind of a outsourced, insourced kind of a mix-up.
Mm-hmm. Okay.
Yeah. Thank you, by the way, for the talk. I myself is, of course, in the automotive, so I know a little bit about this, but I work on the trucks, so it's different quite. But one of the things that you mentioned in the beginning that we have been good at fixing plates and stuff like that, bolting down them and so on, and now you talk about the software. And unfortunately, we have left over a lot of the knowledge to a lot of the suppliers before, and I haven't what are your thoughts about that? Can you continue on actually relying upon supplier in that high degree as you have done? I know that you have more than we have.
Yes.
And so do you think that is feasible with, especially when you talk about your small 3 layers there, that has some very high implications on how you actually develop things?
Yes, yeah. No, I see a great need to insource more of the development, especially when it comes to this core system. We have to have complete control of both the hardware platform and the software platform and the applications that run on that platform. So we have to be the masters of our domain, if you will.
And that heavily will completely change the business model in the automotive.
That will change the business model. Not many suppliers will be happy with that, but we're not the only ones going in this direction, so they'll just have to get used to it.
Thank you for the exciting talk. I have a question. You mentioned a cycle for development of cars of 5 to 7 years. However, in our industry, Moore's law is a little bit faster than that. So how do you plan to deal with that?
How we deal with Moore's law? Well, we're still so far behind, so we haven't really come to the place where Moore's law doesn't apply. So for us, it's still working. No, we have some requirements that maybe your desktop computer doesn't have. We have a much more rough environment in which the electronics sits. So it has to work from, I think the basic requirements are from minus 40 degrees centigrade to plus 80. And in some areas in the car, you get above 100 degrees. And I don't think your laptop would survive that. So there is, of course, some more challenging requirements when it comes to the electronics in those parts. And that's why we perhaps are not as far ahead in the processor families as we are in the IT systems or PCs or whatever.
I think we have time for maybe 1 or 2 more questions. There was one over there, all the way in the back. Sorry.
Thanks for the talk. I wonder about the interaction part, and now in current cars, the intention or the goal of the user or the driver is only on his or her head and what they think to do. But with autonomous cars, the goal also could be understood or should be understood by the car, and there could be kind of human interaction between the car and the user. Could you elaborate more about the intention of the user and the interaction at the runtime and what they put on the top of the architecture requirements?
I'll see if I understood your question correctly. You were wondering about the interaction between the car and the driver in autonomous cars in general, or in cars in general, or autonomous cars?
What requirements they put on top of the architecture?
Well, when it comes to autonomous cars, there is one of the major challenges is to avoid mode confusion. So the driver has to always know exactly, is this car driving itself now, or am I in control? There cannot be any question about that. And that puts a lot of requirements on the interface. It has to be really clear, and you have to have preferably multiple ways in which you tell the driver that now the car is in autonomous mode, and now you are in control.
Yes, but even during the autonomous mode, the user needs could change. For instance, they can change at the runtime their route, or so there could...
That's true, yeah, sure.
So there is a need for kind of interaction to support this at runtime or during the drive to support the user needs and the interpretation of their intentions or goals or whatever.
Yeah, sure. There will be some things that you will be able to do in autonomous mode that you are not able to do when you drive the car. So for our cars, for example, if you have a TV built in, you cannot watch the TV while you're driving. But in autonomous mode, you can do that. Also, the navigational system. I mean, if you enter another destination than the original one, the car, of course, will have to adapt and reroute and do all that kind of stuff. But I don't think that's the tricky part in the autonomous cars.
Thanks.
Okay, and the last question was here with Ivica.
In car industry, there are a lot of standards you have to comply with, and how it will be with development with software? Do you have complete freedom, or do you expect many new standards?
There are a lot of standards when it comes to software platforms already in place. We have the Autom, for example. But we see that the Autom software platform standard is something that applies, in our case, to the mechatronic nodes mainly. And we will have more freedom to choose whatever platform we want in the core system. So we're looking at, of course, fairly known platforms like Linux and QNX to have that in the core system. When it comes to other standards, for example, ISO standards for system safety, they apply, and they will be, over the next few years, there will be more requirements. There will be an update to that standard, of course, and there will be more requirements when it comes to autonomous cars. So there is a lot of that stuff that we need to take into account, and we try to do that as good as we can. And of course we will succeed, but it's a challenge.
Well, let's thank our keynote speaker one more time. It was a great talk,
Thank you
as
very
I
much.
promised.
Thank you.
And here's a small token of appreciation for...
Oh, thank you very much.
Thank you.
Thank you. Chocolate, I hope. Oh, it was chocolate. Oh, nice.
All right, thank you.
Thank you very much. Thank you.